enolates and enamines. So they're really ions, okay? Remember that the enolates, right, enol, okay? And then enamines is the same concept, but for a nitrogen-containing functional group. So we'll be talking about that, and so we'll just kind of start by introducing the enolate. So what is that? Again, referring to, so if you break up the name again, that enol, right, is a double bond, right, next to an OH. That's an enol, okay? But remember that that really comes from when you have a carboxylic acid. So you can either have, right, aldehyde as shown here, a ketone, but you can also have, right, an ester, right? There's other functional groups that also have this double bond O, right? Lactams, lactones, right? The anhydride has the oxygen in the middle, but there's a number of different groups that fit into this category of being able to produce the enolate, right? So why is it an ion? Because I'm not talking about an OH, right? I'm talking about an O as an ion, right? So oxygen here, right, has a negative charge. It's an ion. So the enolate is this one right here. But again, it comes from, right, having the carbonyl, right? Here's an aldehyde as an example. And what do I have to react this aldehyde, ketone, ester with? But a base, because what's a base going to do?
It's going to remove the hydrogen.
Remove a hydrogen, right? So bases deprotonate, and remember they deprotonate where? Not the hydrogen that's coming off of the carbonyl, but the alpha position, right? So what's going to happen is the base is going to remove one of these three hydrogens, leaving, right, the carbon as a carbanion. But of course, carbon doesn't like to have a negative charge. So what's going to happen is there's a resonance where you can move the negative charge over to the oxygen. And that's really the driving force behind, right, this enolate type of reaction. Does that make sense? What's happening here? So you start out with a carbonyl with an alpha carbon that has hydrogens. That base is going to deprotonate at that alpha position, okay, and then you have a resonance which is going to give you the more stable ion. So this is more stable than this. Do you understand why?
Yes, because the oxygen is more electronegative.
Yeah, oxygen is more electronegative than carbon, right? So carbon is not the best option to carry the negative charge. Oxygen is. Does that make sense? So, because again, you want to be able to look at these molecules and understand where to go, right? Where do I get, from point A to point D? Because there's going to be a lot of steps that we're going to have to follow, but this is the first one. Does everybody understand so far? That alpha position, right? So again, that oxygen is going to be the place where that negative charge is going to be best, right, carried. So the enolate ion. Okay, and so again, this is showing you then what can you do once you have the enolate, right? Well, you can do a nucleophilic reactions, right? By having that electron pair, you can make a number of different reactions. And so they're just showing you a few here. So SN2 reactions, right? So nucleophilic substitution, you can see the nucleophile is going to attack, leaving group is going to leave all in one step, right? And so you've just formed new bond. Right? Okay, and of course, bromide would be your ion from the leaving group, right? You can even do nucleophilic addition, right? Again, you have a nucleophile. The nucleophile attacks a carbonyl on another molecule. That opens the double bond, right? Again, we're doing that a lot in chapter 18, right? Or I'm sorry, chapter 16. Okay, so can we do it with chapter 18 groups? Now, they're not just nucleophilic additions, they're nucleophilic additions / eliminations, right? So you can use these enolates in that as well. Okay, because what's the role of the enolate? What is its role? it doing?
Nucleophile.
It's the nucleophile, right? So it can do nucleophilic substitution or nucleophilic addition, right? So it is the nucleophile that we're trying to form with these enolates. And so probably the most recognized reaction involving enolates is called the Aldol reaction. So as the name kind of implies, ald from aldehyde, all from alcohol. So the product is going to have both a carbonyl and a hydroxyl group. Okay, so we're going to see how that happens. And so, again, this is probably, the most common reaction. So if you look up enolates, most likely it's going to show you an aldol reaction as an example. These can be with same or different compounds, meaning that you can actually start with the same starting material and create the aldol, or you can have two different and make the aldol. So we'll see examples of both. And these can be catalyzed by either acid or base, but the base is more common. Why? Because what's the base going to do? Deprotonate and form the enolate, right? Which is the key to all of these reactions. So it is more common to see the base, because ultimately that's what I'm trying to do, form the enolate, and that requires a base. But you can do it in acid as well, so you might see that as an option. Okay. So what does that aldol look like? That product of the aldol reaction. So the product is what we call a beta hydroxy, right? So again, remember the alpha is next to beta is the carbon next to that. So it's basically position 1 and 3, right? If we're looking at where the carbonyl is. Okay, so again, right, we're looking at two molecules that are identical. So that's one option, right? Both of these are ethanol, two carbons with aldehyde as the functional group. One is going to serve as, right, the carbonyl that's going to be attacked. The other is going to serve as the nucleophile. Does that make sense? So one of these hydrogens is going to react, right, with the base. Deprotonation is going to happen, right? So you can imagine that now you have your nucleophile at this carbon attacks the double bond opens, right? So what do you get here at the beta position, right? Beta, right? Alpha, beta. Does that make sense of the new bond? You follow? Right? So if the alpha carbon attacks the carbonyl of the other ethanol, this is now beta, right? Because the chain is elongated, right? 1, 2, 3, 4, right? 1, 2, 3, 4 carbons, right? 2 ethanols coming together, 2 and 2, right? Just basic math, right? You make a 4-carbon chain, right? Does that make sense? So alpha is the next 2, beta is going to be the one next to that, and that's where the OH is at. Where did the OH come from? Right? When a carbonyl doesn't have a leaving group, it opens and becomes an alcohol. So again, we've already seen that in chapter 16 over and over and over again, right? Does that make sense? So you always get this beta hydroxy. In this case, it's an aldehyde, but you can also get a beta hydroxy ketone. So here you have 2, right, propanones, which is also acetone. So again, if I look here, right, they're the same. One is going to serve as my carbonyl that's going to be attacked. The other is going to provide the alpha carbon, right? Again, the base is going to deprotonate, right? This is the nucleophile, so I'm going to attack, open. Do I have a leaving group? It's a ketone. So those carbons are now good leaving groups. So what do I get? An alcohol, right? Does everybody follow? This is, again, it's very similar to what we've been doing with chapter 16.
So instead of it adding from the chain, it adds from that carbon, so it makes those 2 methyl groups, or the 2.
Well, it's adding to, in the case of acetone, that carbonyl is in the middle, so it's adding to the second carbon in the chain, so that means the CH3, they're just putting it down here, Because the longest chain is now really 1, 2, 3, 4, 5, right? And this methyl here is just become a substituent instead of being part of the main chain. Right? But again, if you look at, right, the structure, it was 1, 2, 3, right? Or sorry, yeah, 1, 2, 3, 4, 5, right? Again, the other methyl goes down 1, 2, 3, 4, 5, right? You see the longest chain there. And the relationship again, right? The carbonyl, then the alpha, and then beta is where you get your hydroxyl group. It's always the same. Does this make sense? And this is, again, the Aldol reaction always gives you this product, the beta hydroxy. And again, it can happen with an aldehyde or with a ketone. And that's the Aldol. Most common reaction when you deal with enolates. All right, and so this is again just showing you what's going to happen. The base shown here is a hydroxide. It's going to deprotonate the alpha carbon, the carbon next to the carbonyl. Right, it's going to leave it again, right, with that negative charge, which can be, right, in resonance with the enolate. But it is the carbanion that attacks. Now why? Why wouldn't the oxygen attack? Right? If I'm saying these are your two resonance, why isn't it that this oxygen attacks? Why? Why do I make a bond? What's the purpose of making a bond? To get a full octet, which means that there's stability, right? You're making something more stable. Would you say oxygen here has a full octet, right?
Yes.
Yeah. So it's okay. I mean, it's not 100%, fine, but it's okay. What about the carbon? Does it have a full octet? Yes. But what's wrong with it here? It is not electronegative, so having that pair of electrons, even though, yes, it is a full octet, it's really not built to carry the electrons. Oxygen is, because it is, right, the second most electronegative atom on the periodic table. Carbon, not so much. So it is really the carbon who has the driving force to do this reaction. The oxygen is actually okay like this. Does that make sense? Because you have to figure out what's going to be the atom. I saw that a little bit on the exam. Some people, even though they picked out what molecule was the nucleophile, they were not sure which atom was going to do the attack. And do you understand what I mean, right? This is the molecule, right? But is it this atom or this atom, right? You got to pick correctly. So I just want to make sure that's clear. Yeah.
And these are reactions, since they are in resonance,
these are not. These are the same molecule because they are in resonance. So they're converting into each other very rapidly. But what I'm saying is this one, when it gets the opportunity, is going to want to get rid of those electrons. Where the oxygen, it'll be happy to hold on to those electrons because of its electronegativity. So here, it actually would not react, be in a hurry to react. So if I was going to extract this intermediate, what would I see? This molecule, right? I would see very little of this if I was trying to extract it, right? Because it's too unstable. But instability is good for reactions, right? So the carbon is going to be the atom you want to think of as the nucleophile. Does everybody understand the difference between being able to pick out a molecule that is the nucleophile and picking out which atom in that molecule is actually going to be doing the attacking? That is something I did see a bit of on the exam in question 2. So the people that missed points on that question, some of it was that they weren't sure. Is it the nitrogen or the oxygen, right? Does that make sense? Because there was options like that. So here, I'm trying to tell you, it's always the carbon, right? That's going to be the nucleophile. In Aldol reactions, it's always the alpha carbon acting as the nucleophile. That's not going to change. It's a constant in this reaction. So make a note. Does everybody understand what I'm saying? If you don't understand, just ask me. You understand what I'm trying to get you to look at. Because that's where confusion comes in, because you're looking at this and saying, it's not matching with what she's saying. And sometimes I say funny things and weird things and I'm wrong, you know, I mess up, but what I'm saying here is the truth. That carbon is always the one acting as the nucleophile, not the oxygen. So you do want to make sure it matches with what the paper is showing you, and I think it does. Okay? So that's the aldol. And then of course you do, right, have to finish up right here, okay, with just the hydrogen. So that's what the third step is. You just protonate, excuse me, give that oxygen to give you the alcohol. So that's step 3. It's a 3-step reaction. Now, what if I had an acid as a catalyst? So the previous slide is the most common method, using a base as a catalyst, but this could happen with an acid as a catalyst. So what would the acid do? What does it always do? Protonates, and again, protonates what, right? The oxygen, right? Oxygen is going to be the one that gains the hydrogen. And then again, it's in resonance, right, with the enol. So you could do that as a first step, and then the second step, okay, which is shown here, you're going to transfer, okay, so you're picking it up here, and then making, right, your carbonyl oxygen as a, right, ion. So you could do this. So there's this proton transfer that's going to happen. So that's when an acid is present. So then you still, though, right, you're still preparing, and the next is going to be the enol attack, followed by the transfer of the anion. So that's what's shown down here. They kind of put it all in one picture for some reason. But again, the anion, right, retrieves the hydrogen that you got in the first step. Okay, those electrons come back to the double bond, and then the double bond comes and attacks the carbonyl, and then the carbonyl opens to make your beta hydroxyl complex, right? So you see why acid is not the preferred catalyst, right? So, yeah.
You don't have the double bond in here.
You don't have, which double bond, sorry?
Well,
This one?
Yeah.
It's just in resonance. It's just, I mean, they're kind of, they bunched it all together, but what they're saying is this is in resonance with the double bond being here. So, but my point was, this looks pretty complex, right? And it's 4 steps, where the base is 3 steps. And, you know, the least amount of steps means that there's a preference, right? So that's why base is a more common catalyst than acid for these reactions. But it does work, you know, under acidic conditions. You would get the product, same product. But it's not the preferred method. And hopefully you can see why there. So on the exam, I'm not going to use acid as a catalyst. I can't guarantee what Al is going to try to, you know, pull with you. But on the exam, right, I'm going to get you to use the most efficient, which is using a base as a catalyst. Okay? So, but it is possible to use the acid, but the base is preferred. All right? So the aldol, again, right, the product is this beta hydroxy aldehyde or ketone. But what's going to happen is that a lot of times, again, when we're analyzing what products we get, what scientists or chemists were seeing is that you weren't getting the beta hydroxy, you were getting a double bond, which they called the alpha beta unsaturated product. So what's happening here? Well, what's happening is that you have this alcohol, right, next to a carbon that has hydrogens, right? So what actually happens in these reactions, these aldol reactions, is that a water is eliminated. So once you get your beta hydroxy aldehyde or ketone product, a water is eliminated. So what we actually see, unless we control for this, If we just let the reaction run its course, we end up with the alpha beta unsaturated, a double bond which comes from water being eliminated, right? So why would that be? What do we use when we want to eliminate a water? Base plus heat, right? Base plus heat. Right? Guess what we have, right? A base. Usually, it's the most common, right? And you usually do this reaction at a little bit above, right, room temperature, so it's a warm solution. So all of the conditions are for the elimination to happen anyways. Does that make sense? So again, Al likes to do this a lot. They won't ask you for the beta hydroxy. When they say what's the product of this reaction, they're assuming the elimination is going to happen. And it does happen, again, unless you control for this. So how would I control for this? What do you think?
An ice bath?
An ice bath, right? I need to control the temperature of this reaction. That would be a very important thing if I was trying to get, right, the beta hydroxy. Does that make sense? So, there's ways of getting around that. But in general, the dehydration is preferred. So the equilibrium constant is towards the elimination product. Okay? So that's it's explaining, okay, what could happen, right, under these conditions. So far we've seen, right, two of the same molecules reacting with each other to form these aldol products. But what if I don't have two of the same? That's called crossed. I think the book also uses mixed sometimes. So again, crossed or mixed means that you have one kind of molecule reacting with another kind. For instance, a ketone reacting with an aldehyde. Does that make sense? So before we were saying acetone and acetone, right? Ethanol and ethanol. That's the same molecule. If there are two different molecules, then it's called crossed or mixed aldol reactions. And again, here's a ketone reacting with an aldehyde. Now, can you imagine here, right? If we looked at this reaction, which one has to be the alpha? Right? The alpha carbon that does the attacking. Which one has to be?
Go on either side of
Which one? The ketone or the aldehyde? The ketone, the aldehyde, would you agree, these hydrogens are not available for deprotonation, right? There's no carbons here. Does that make sense? With hydrogens. Here I have two of them, but gladly they are identical, right? So one of these, right, either one, they're identical. This one is going to attack open, right? So that's why the product actually has, right, the ketone came from the nucleophile. The alcohol came from the aldehyde carbonyl. Now, this gives you one product. Imagine that I had an additional carbon on this side. Now, both sides are not identical. They both contain alpha carbons. How many products would I get? 2. Right? Now imagine that my aldehyde also had a carbon. Now how many products would I get? So, right, crossed or mixed can be very complex reactions because as you add more alpha positions, you're also adding more possibilities of products, which lowers your yields. Yes?
For you have, I would say, the two carbons almost have one on the other end, and on the aldehyde has a carbon. Would the percentage of each product
Be identical, like 25 or 30, 30, no. No. So aldehydes are considered more reactive than ketones. So what that means is if the aldehyde, right, can have the alpha, it's going to be the one. So you'll see a higher percentage of that product. Okay? 2 carbons versus 1 carbon, is there a preference? If I have a methyl on one side and an ethyl on the other side, is there a preference between the smaller, right? A smaller nucleophile often leads to a higher yield. So even though it won't be a huge change, if you imagine that maybe it's not an ethyl on the other side, but it's a, you know, sec-butyl or something a bit more complex. So again, these can be much more, you know, the products can be different. So this is much more complex than having the same starting material. Then you only really get one way to go. This gives you lots of possibilities if you have the right mix. So in this case, the way it's drawn is very simple, but it's not always. And Owl likes to do the complex ones where you get 3 or 4 products. Do you understand where I'm going with this? Right? So if your chain, right, it makes a difference, right? Because you have 2 alphas that are not identical. Does that make sense? And then if your other product that you're attacking also has alphas, right? Does that make sense? Then you have to take into consideration that maybe, you know, if you have a ketone like this and reacting with that, there's also an alpha over here. So you have a mix of what can be present. So the more alpha positions you have, the more products you're going to have. That's kind of the, you know, shortened version of that story. In a nutshell, the more alpha positions you have, the more complex your product pool is going to be. You're going to have more products. Okay? But often we do try to maximize the yield. So we'll use reactants that do not have alpha positions. So for instance, formaldehyde is a great one because there are no alpha carbons. Okay? Benzaldehyde is another good one because the carbon that's alpha already has 4 bonds to other carbons, so there is no hydrogen either. Okay? Furfural, I just let me say that's a fun word. Furfural. Again, if we look at the alpha position, 1, 2, 3, 4 bonds already, no hydrogen, right? Okay, and then this dimethyl 2,2-dimethyl propanol, same thing, right? This carbon has already 4 bonds. There is no hydrogen in the alpha position. Does that make sense? So often you try to control the crossed or mixed aldol reactions by choosing reagents that do not have an alpha hydrogen available. Okay, that way you can control the number of products you're going to have. So, and it says there, the more reactive carbonyl is the aldehyde. So often the aldehyde is going to be the one being attacked on the receiving end of the attack. So if you have to choose, right, there's an aldehyde and a ketone, which one is going to act as the nucleophile? The ketone. The aldehyde gets attacked by the nucleophile. Okay, so just a few points again. If you're doing cross, you have to consider these things. When they're the same molecule, it's a lot simpler. Nitro groups can also have an effect on this. So remember, I think we talked about nitros before, but in case we haven't, right, this is NO2. So NO2 as shown, right? So it's going to have a double bond O and an O. Okay, so it's an ion, but it's an ion that's neutral. Would you agree? The negative charge and the positive charge cancel out. That's called a zitter ion. So the neutral, another fun word to say, zitter ion. Yeah, so we learned 2 fun words today. I'm going to try it with my son. Say, can you say zitter ion? He's so cute. Can you say furfural for mommy? Yes. So nitros also can participate in these aldol reactions. So why? Right? So if we look at this, where would this fit in? Well, this nitromethane has an alpha carbon, doesn't it? That alpha carbon has hydrogens. So a base could come in, right, deprotonate the alpha carbon, and then you see that you can do a similar type of enol type of resonance, right? Of course, this is not an enolate because it has a nitrogen, a nitro group, but you can see how there's a stability in the resonance just like there is with the enolate. And so you can do this reaction. So nitro groups then can be reduced, okay, to the amines. And so often this is an intermediate when you're trying to make amines as a product. So the amino group came from the nitro. So So again, it's the carbon doing the attacking, right? The alpha, attack, open, right? Leaves you with the alcohol. The nitro group with the carbon is your nucleophile that was added, but then this can be reduced to the amino group, right? NH2. And you see that that's H2 with the nickel. That's just catalytic reduction, right? Which we've learned with other alkenes, for instance. So just another possibility for the nucleophile of these reactions. And of course, these reactions can also be intramolecular. So there are incidences where, again, you'll have, right, alpha carbons, and then somewhere further down the molecule, there's also a carbonyl, so you can attack, right? But remember, what's the golden rule? How many members in the ring? 5 or 6.
Yeah.
Right? So again, when looking at the possibilities, alpha 1 or this alpha 3, right, you got to count. 1, 2, 3, 4, 5, 6, 7. Is that a good one? No. Right? 1, 2, 3, 4, 5. Is that a good one? Yes. Right? So this is going to be formed, the 5-membered ring, but the 7 will not, because it has to be either 5 or 6. It can't be 4 and it can't be 7. So you do have a possibility of doing these reactions, intramolecular reactions, and getting cyclic, but 5 or 6 membered are the ones, right, the magic numbers there. Okay, the others are not successful. All right, so these are Aldol reactions. Any questions? This makes sense initially, until we start doing some problems on Aldol. But then you let me know and I can clarify those as well. But again, aldol are probably the most common reactions for these enolates. Okay, but another type of reaction is called a Claisen condensation. So now Claisens start out with esters. So aldol reactions start out with aldehydes and ketones, right? Claisen reactions or condensations start out with esters. Now remember, esters can also form enolates because they're going to have, right, the carbonyl and an alpha carbon, right? The alpha carbon in one is going to attack, and the carbonyl of the other ester is going to receive, right, be on the receiving end, and then you get the new product. So what's that product look like? Right, so it is now alpha, or let me do it down here since it's labeled. Alpha, right, is next to alpha, beta, not hydroxy, but keto, right? Beta keto ester, right? Alpha, beta. There's a ketone at that position. So why is this different? What's different between an aldehyde and a ketone and an ester? It's the difference between chapter 16 and chapter 18. What's the difference? What do I have in chapter 18 molecules that I don't have in chapter 16? Leaving groups, right? An ester has a leaving group, right? So you're doing the attack in the same way, attack, open, but what happens next? Close, leave. And that is why you don't get beta hydroxy, you get a beta keto. Does that make sense? So these reactions, would they work for aldehydes and ketones? No. Aldehydes and ketones don't have leaving groups. So I cannot do a Claisen condensation with an aldehyde or a ketone. Does that make sense? Could I do it with an acid chloride? Could I do it with an acid anhydride?
Yeah.
Yes, they have leaving groups, but the answer is no.
Because they're active.
They're too reactive. So these reactions, they don't tend to be successful with the acid chlorides or anhydrides. They work best for esters. But technically, yes, they do have, right, a carbonyl next to an alpha carbon and a leaving group, but they are not the right fit. Their reactivity is too reactive, which is a problem. also. So Claisen condensation, so now you have ethyl propanolate, and again, two of the same molecules, so this has the same type thing. You can have same molecules reacting together or different molecules reacting together. And so if you look at here again, right, there's an alpha here, right? That alpha is going to be deprotonated by the base, right? So this is going to attack, open, close, leaving group leaves. So notice that in the product, one, right, of the ETO is gone, right, as ethanol, the leaving group. The other one is left still there, right, because it's coming, right, coming from the nucleophile that's attacking. So I think they show you in a future stuff. Oh, maybe not. Don't want to get too far, but again, I just want to kind of show you that, right, the part that gets attacked loses the leaving group, but the one that does the attacking, the nucleophile, retains the leaving group. So the product is still an ester, right? Because the OET remains in the part that comes from the nucleophile. So the product, again, is a beta keto ester. So what's that water and acid doing as the second step? We know the first step is a base. It's deprotonating. What's the second step doing? Protonating what?
The carbon and the carbon.
The ethanol has nothing to do with your major product, actually, but it's going to provide the hydrogen necessary to make it an alcohol, right? The leaving group. So Al also likes to ask for that, like ask for just the ions and things like that. So just kind of, so you're prepared for what gets the hydrogen. All right, so it's showing you here again, right? So you have a base. The base deprotonates the alpha carbon of one of your esters. Okay, and again, you have that enolate, but remember, it's the carbon that's going to do, right, the attacking. The nucleophile is the carbon, right? So that's going to attack and open, which gives you that tetrahedral intermediate, but we know this is going to collapse, right? Because the double bond is going to close and the leaving group is going to leave. Okay, so that's what's going to happen next. It's the collapse of your intermediate, right? So again, the double bond reforms as the leaving group leaves, and you have your, right, double bond O. So your main product is formed, but you need to do one more step, right? The protonation. So that's the complete reaction. So this is Claisen condensation. So esters are involved. And of course, this can also be intramolecular, and this gets its own name. It's called a Diekmann condensation instead of Claisen, but it's really just an intramolecular Claisen. So again, same molecule with two esters, right? And the distance between them is important. Again, right, the alpha position, 1, 2, 3, 4, 5 carbons away, right? It has to be 5 or 6. So the Diekmann doesn't work for every molecule. It has to be able to form the 5 or 6 member ring. And then again, right, here's a 5 member ring. And you do get, again, right, this is alpha beta keto ester. It's only cyclic because it's an intermolecular ester, diester, excuse me. So it's same, right, base is the first step, followed by, right, the acid, water, HCl, to protonate the alcohol. Okay. But of course, right, those are the same molecule. What if I have different molecules? They're crossed, Claisen, right? Crossed, meaning they're two different. And again, we run into the same problem. If there's multiple alpha positions, this can get very complex. And so we tend to choose reactants that don't have, right? So ethyl formate doesn't have an alpha carbon, right? Diethyl carbonate doesn't have an alpha carbon. Those are oxygens there, right? Diethyl ethane dioate, right? Again, right? They're together, the two carbons here, but there's no alpha with hydrogens. And then the ethylbenzoate, we already talked about how benzene doesn't have any hydrogens available. There's already 4 bonds to other carbons. So we tend to use these in order to maintain the number of products small so that the yields make sense. Otherwise, it doesn't make sense to do a reaction if you're going to get 5, 6, 7 products, right? The yield is going to be so low. So, but you can do crossed or mixed Claisen condensations as well. So here's an example. Methylbenzoate, right? Reacting with methylpropanoate. So which one has the alpha? So again, methylbenzoate, this is a benzene. I know it's not drawn out, but there is no hydrogen coming off there at the alpha position, right? So the alpha has to be this one. Would you agree? There's only one way to do this. So attack, open, close, leave, right? So this is gone. Or sorry, from here, right? This is gone as the leaving group. And you form, right, the beta keto ester as your product. So you just get one product this way. Does that make sense? And the ester without the alpha carbon, okay, so this one here, methylbenzoate, is generally in excess. So the limiting reagent is the one doing the attacking, the nucleophile. So that's just something to consider there. So if we were doing this in the lab, right, we would have to figure out, and usually is the one without the alpha hydrogens that is in excess. So just giving you again the routes here. So what can we do with this, right? So one of the things we can do with the Claisen, because of the second ester, we can actually make ketones from this. So what happens is you do the Claisen just like we had, right? The base is going to deprotonate, right? Attack, close, leave, and then the alcohol completes the leaving group, right? So that's the Claisen steps that we covered so far. Then to that, we can add 3, 4, and 5 here, which I like to call SAT. Get it? SAT. Right? SAT. So supenification, that means that you're going to react your ester with a base. Okay, when you do that, you form a salt. So you remove, right, the leaving group in a sense by leaving it with a negative charge, and you're going to end up with the sodium, so that's a salt. And then you follow that with water and HCl, which makes, right, the product acid. Right, so it's supenification forms the salt, which is the soap, and then you acidify, right, acidification, to make it a carboxylic acid. Okay, remember that beta keto acids can undergo thermal decarboxylation. We talked about that in chapter 18. I told you that we wouldn't have to really know it for the exam as far as reaction, but now you do because it's part of this mechanism. So this, right, the COO becomes carbon dioxide, right? Where does this hydrogen go? Right, COO, right, that's CO2, but there's a hydrogen. Where does that hydrogen go? Back over here, right? When I break this bond for this to leave, this carbon needs another bond, and it's going to take the hydrogen. So it's kind of a perfect little doesn't need anything else but heat. You literally don't need any other reagent. That's it. It's a warm hug. That's what Diego was doing, right? Thermal decarboxylation. That's all you need is heat. It has everything else it needs built in. Does that make sense? And so what did I end up doing? Removing my acid group, which now means all I have is a carbon chain with a carbonyl, which is a ketone. So if you do a Claisen followed by 3 steps, SAT, right, 5 steps altogether, you end up with a ketone. And so it's a very common attachment to these Claisen reactions. Now, would this work for the aldol? can I tack in the SAT to the aldol? No, I don't have this part. That only comes from the ester. So these only work for the Claisen, do not work for the aldols. Because aldols already start with an aldehyde or ketone. Okay? And so this is just showing you that the reaction, right? I think this is the slide I was kind of looking for, because it just shows you that, right, the part, excuse me, in the ketone that you get as your product of the 5-step, Claisen plus SAT, okay, a part of it comes from one of the esters, right, and the other part comes from the other ester. Okay, and so it tells you that this part came from the carbonyl, they got attacked, and this part came from the enolate that did the attacking, the nucleophile. So you actually can predict ahead of time what the product is going to be very easily. Okay, so these are very useful reactions, right? Predictable reactions are nice in organic chemistry, so that you know you're going to produce what you want ahead of time. So, all right, and this is where we'll stop. We'll talk about the enamines next time. And again, I told you that this is going to go on for 4 classes, so please use the time to ask me questions. So if you don't feel comfortable moving forward to the enamines next time, let me know. Let's do some examples. Of course, you're going to get a challenge next time, so what is it going to be on? Aldol and Claisen. So, okay. That's all I got. That it's really continues to be important for you to figure out, right, your nucleophile, right, what's doing this, okay, attacking of the carbonyl. So this is really the basis for the reactions, all of the reactions in this chapter, okay. And so now, right, we're going to be dealing with the enamines. So now you have nitrogen participating, right? So we saw aldehydes, ketones, right? Esters, they have oxygens, right? The carbonyls there. Now we have nitrogen. And in these reactions, there are going to be those secondary amines. So remember, we get a reaction with primary amines, but that doesn't give us this product. It gives us a Schiff base, right? So that's not the same. So secondary only in this chapter, secondary amines. The 2 most common reagents in these reactions with the secondary amines are shown here. So pyrrolidine and morpholine. Okay, so again, the nitrogen attached to 2 carbons, right? That's secondary, which means there's only 1 hydrogen available, right, to be exchanged, which means the product is a double bond at the alpha beta position. So when you do these reactions, so let's again figure out, right, we look at this and we have to come up with what is the nucleophile. So who's going to be doing the attacking?
The nitrogen.
The nitrogen, right? Does that make sense? All right, and what's the nitrogen going to attack?
The carbon.
Who's going to get attacked? It feels so violent, like organic chemistry is so violent. The attack. Who gets the attack?
The carbon.
The carbon, okay, yes. Now, which carbon?
The one right next to
Which carbon? Right, so the nitrogen is your nucleophile, right? Who's going to attack who?
Alpha. The alpha carbon.
Not the alpha carbon.
The carbon is carbon.
The carbonyl, right? The nucleophile is the alpha carbon from the previous reaction. So, right now we don't have an alpha carbon being involved in this reaction. We have the nitrogen as the nucleophile and the carbonyl being attacked. So remember, nitrogen has the pair, right, of the lone pair there. Right? So this is what we would be looking at. Does that make sense? All right, so when I do this reaction, what do I get as a product then? All right, so initially, what does that look like? Right, so carbon chain is still the same, right? The O is now an ion because you're transferring the pi electrons over to the oxygen, allowing for a bond between the carbon and the nitrogen, right?
Because when you attack
Right, so that's what you have initially as the product, but we know this isn't done. When I look at this, it should be clear. All these charges hanging around, that's not final, right? That's not what my product is going to look like. So what is going to happen from this point? Right? You're going to have some exchanges of hydrogens, right? Initially this hydrogen, right, with this oxygen, right, to make an OH. And then what? So now I have OH, right? I have nitrogen, right? This seems like a fine product, but I know this isn't it. Why not? Because this is secondary. There's hydrogens at this, right, alpha position. It's identical on the other side, so it doesn't matter which way you go with this, right? So what's going to happen in these reactions is that the OH and one of these neighboring, right, alpha, or now it's at the beta position there, next to the nitrogen, the OH, they're going to be, right, alpha beta positions here are going to give you a double bond, right? That's an elimination, and then you have your nitrogen, right? And this is your enamine, right? En, right? And this is the amine. Does that make sense? The en is the double bond between carbon-carbons, and the amine, of course, is the nitrogen. Yeah, Ruth?
I'm sorry, why does the alpha and the beta make a double bond again?
Because that's where the OH, the neighboring carbon, is the one with the hydrogen. So this is where the position where the double bond can happen, because you're eliminating this water. This is water, right? OH. So you're basically removing a water here, right? Here you're exchanging these, right, between what you have there. It's a little bit more complex than that, but I'm just kind of, right? Eventually that's what happens. That hydrogen on the nitrogen goes to the oxygen to make it an alcohol. There's a few molecules that have to come and
then we
help
have
you with
neighboring
that.
hydrogens that then attract the OH, making the water.
Yeah, so because they're neighboring like this, okay, they can form water and then cause your enamine, right? Does that make sense? So do the other one all by yourself. Please put yourself. It's been a problem in my other class too, so I'm more sensitive to it.
Is that kind of
Please don't be tempted. All right, so do the other one all by yourself. So again, now you have another issue. You have two potential nucleophiles.
That's
So think about it, think about it, think about it, think about it. As I have my phone out just like this.
Daughter don't have to email me, so you can fuss.
It's her fault. Doesn't she know you're in class? And what is she doing? She could be in class. Text her back and say,
you should go to her class. You should go to her office and give her a stern.
she's not in there, she's in her class. What is she doing?
You should
must
go to
have
her
an
class and give her a
exam. You've got it, you got her caught on camera on that too. So again, right, you have a little bit of a choice in there, but again, what are we focusing on here? Nitrogen, right? So do the bottom one by yourself. Come up with a plausible product. Think you have it, you can pencil down, I'll come around just to see. I'm rated, but if you don't think you have it, just, keep holding your pencil. As long as signals you might be done. You might be done doing what you think.
I don't know. That's what I don't know. You just connect
You attack the oxygen. The nitrogen. The oxygen like those electrons way more than I just told you there's two things there, but the nitrogen should be the target. You just want, I see you did everything correct, but it should have been the other.
I just missed your,
Yep, I'll be back.
Book you reading.
Already missed most of
The nitrogen is going to be more nucleophilic than an oxygen, right? So, right, nucleophilic, because oxygen is more electrophilic, right? It likes electrons more than nitrogen does. That's correct. You got it correct. Did you get scared?
Yeah.
No, you attacked with the nitrogen, so you were right. Some people attacked with the oxygen. So that shouldn't be. I just told you though, that is confusing. I mean, now you do have something else there that might confuse you, but nitrogen is more nucleophilic in this case. Right? If this was a negative oxygen, then that would be another story, right? But this is not. This is a happy neutral oxygen with its two lone pairs, just like it likes to be. Just like it likes to be. Okay, but again, right, the nucleophile, you have to make that determination first. If you like are not certain about that, that kind of, compounds the problem. So you have to figure it out. In this case, right, I mean, we're working with nitrogens, but in general, nitrogens are going to be more likely to act as a nucleophile. They would be willing to share the lone pair. The oxygen as a neutral, right? Oxygen as it's shown in the molecule here, it's really happy, and it's going to keep its both of the lone pairs. It's not going to want to share. So yeah. No. Right. So when you do that again, right, what's going to happen is your oxygen is going to be negatively charged. It now has that extra pair, right, and then the nitrogen is going to be here carrying its ring, right, and the charge. And then again, it's a little bit, right, of a motion of these, but eventually this hydrogen, right, and this oxygen are going to come to an exchange. So this is actually going to be an OH, and this is going to be the nitrogen, right, as neutral. And then what you have to remember is that this OH, right, and if there's neighboring hydrogens, and it can be on either side, right, this is symmetrical if I do like this, so either side is going to be fine, but one of these hydrogens is going to provide, right, the water that you're going to lose, right, this is going to be minus water, condensation reaction, which will then give you the product of elimination, which is a double bond. So again, ene, right, and then the amine. That's how you know you did this right. If you're not getting a double bond between a carbon and a carbon, and then the nitrogen, neutral nitrogen, then there's something that you're missing. So this is really the basis for this part of the chapter. So this chapter is both enolates, the ions we talked about last time. Okay, enol, right, double bond with the OH. Okay, here is double bond with the N, right, so enamines. So that's why they're talked about together. So. And of course, if you were just asked for the product, you just want the enamine. You wouldn't have to go through the process. I just want to show you how you end up with that double bond adjacent. Double bond. So these look prettier, but It's still same thing. Just looks pretty.
Wait, go back.
Wait, yeah,
Oh,
that's the
go back.
oxygen.
The bottom product's wrong.
Yeah.
Yeah, I just copy paste.
Oh.
I copy paste there. I mean, the reaction is exactly correct. This should just be a 6-member ring. So I mean, that, you know, this and this is correct. I just copy paste it. Copy paste error.
Plagiarism.
Well, the first year that I did it, I just had the same, I didn't use the 2 different ones, and then I think I just copy pasted the answer from an old notes. But do you understand what they caught me on?
Yeah.
I used that same one with this one, right?
Yeah.
But I had changed by adding the oxygen there so that we could have the discussion we had about which atom should be the nucleophilic center.
So it's just like something you do
Where
on
is
your
this in our
test.
books?
You just change the.
I do this all the time. I nitpick, and I nitpick. But I always make some error. And now my program that draws my structures is out of date, and I've been waiting for over a year. I should send this tape in as evidence of my unhappiness with it. So I can't even redraw. So now on the exams, you have to get old exam structures, and I can't draw new ones. So is that good or is that bad? I'm not sure, but probably better for you. All right, so now what can you do then with an enamine? So why are we talking about it here in this chapter as a valuable reagent? Well, that's because that beta position, right? So again, alpha, beta, right? So I can actually transfer these pi electrons and make a new bond between my beta carbon in a new carbon chain, which is really the initial part of the Michaels addition, which is going to be our next major reaction in this chapter. Okay, so do you see what I mean there? So because the nitrogen has a lone pair, even in its neutral state, right, that can be shifted here as a double bond, stabilizes the alpha position, and allows the pi bond to go ahead and attack, right? This is a leaving group, right? A molecule with a leaving group, an alkyl halide. Okay, and so this is really an SN2 mechanism, right, from here. Like, this is kind of different, but this part is just attack leave, right? That's SN2. And so what you get is this ion, which is the iminium ion. So we're back to an imine, right, a double bond between a carbon and a hydrogen. But guess what, right, we're not finished. You can tell some more action is going to happen, right, more organic chemistry action to come. But again, here I want you to focus. Do you see that that beta position is going to be the one, right, making the bond, right? It's going to be between, this is alpha, this is beta, right? The new bond is going to be here to this carbon here of the alkyl halide, right? And that's what you see the addition, right? 1, 2, 3 carbons, right? 1, 2, 3 carbons. The new group there, the addition to that double bond. So this is an SN2 mechanism, but it allows for a new carbon-carbon bond. Another, right, theme in this chapter, we're making new carbon-carbon bonds in every single reaction in this chapter, so keep that in mind. All right, so what happens next? So if I take that iminium salt, right, again, coming from the imine, the shift base that's forming here, okay, this is a salt, so if I add it to an acid, right, acid in water, a dilute acid, what is it going to do? Well, I'm going to provide some hydrogens, right, and in the presence of water, there's also hydroxide ions, to then release this salt and give you a carbonyl. And again, you don't have, the book does show you the steps involved, but if I don't think it's too helpful, I don't always cover in class. But basically what you're going to do is remove the nitrogen salt, right? And in its place, you get the oxygen. So you form a carbonyl. In this case, a ketone, but you can also form an aldehyde depending on where the carbonyl is in the chain. So the iminium salt in the presence of water and an acid is going to give you a carbonyl. So that's really what we use the enamines for. And these reactions are called alkylation reactions because you're adding a carbon chain, an alkyl, chain. So these are alkylation reactions. Does this make sense what the product is then?
Yeah.
So if you're given something like this, moving the black one around, I think this is the one that works best. So if you have this, right, and you add it to, right, a secondary, like this, right? And then in your reagents here, you're gonna have, right, that H plus in water. What's ultimately the product? Do you know what I mean? Like if you have, I'm sorry, I missed a step. This should be step 2, sorry.
Yeah, there should be a base.
I missed a
first,
step.
right?
If you have, in step 1, like a CH3Br, and then step 2, H plus in water. So got a step there. So ultimately, like this is a common thing that we see. So like Al likes to kind of put it all together, right? So you should keep in mind that you're gonna have the enamine form first. Does that make sense? So the combination of these two, right, is gonna be the nitrogen, right, with the double bond beta, alpha beta, right?
Yes. And then we add.
Right, and then you're going to, right, have this react with this, right? So you're gonna have the CH3Br, right? This is gonna have the lone pair come here, this comes here, and that leaves, right? And then you're gonna have the water too, right, coming in. So this is gonna give you an extra carbon, the CH3 here, right? And with the water, what's gonna happen where the salt is gonna be a carbonyl. So it's totally different from the starting material, but it is a, right, it's a methodical thing. It always happens the same way.
Very repetitive.
Right? So this is now here, right? And the oxygen is now here. Right? And it happens like this every single time. And this is what Al is going to do, right? Ask you for this.
Can we draw the side product too with the nitrogen?
Huh? The side, this is just so you can see where the beta is going to be. But they're not going to want any of this. Al is just going to want this. And they're going to couple the two together like that. So just to keep in mind that this is leading up to this, right? So the enamine formation is just really in order to give you that option to make the new carbonyls. And that's another thing. We've been making aldehydes and ketones, right? Beta keto or beta hydroxy, right? And then the beta keto esters. And now we're alkylating these aldehydes and ketones, making the chain longer, right? Because wouldn't you agree, ultimately all I did was add another carbon? Ultimately, that's all I did. And I went through a lot of stuff there in between. But all I really did is add here. So what's the benefit of that? Where, like let's say I had Grignard. Grignard adds a carbon chain, but what would be the problem? Where is that carbon going to get added to? Not here, but here, right? And that's might not be where you want it. That makes sense? So, ta-da! I feel like it's like magic. It's like magic. It's magical when you really understand. It's like, oh wow, that is really simple. It's like almost like magic.
And all happens
Primary.
For the primary carbon.
Yeah, so it's gonna be it. Well, it could if this had a longer chain, it would still be here, right? Because it's the alpha beta position. You know what I'm saying? Like it's still gonna be that next 2. So it doesn't always have to be position 1. In this example, it is. You're right, but it's just gonna be that position, right? Alpha beta is gonna be actually next to. So.
Even if it was a longer chain.
So that's what I mean. If it was a longer chain, it's just going to be at that alpha beta position, right? Like between those 2 carbons, you're going to have to do the reaction still right there, not further down. That's
So little would really change if it was a longer chain, because it would be.
well, the carbon would be then as a substituent coming off of the chain, not as a like another carbon on the chain. But I guess like I wanted to highlight that we've seen things like this with the Grignard, but we were locked in. We could only add it to the carbonyl carbon because that's what the Grignard reacts with. Now I'm telling you, I can react adjacent to it. I hope all the side chatter is about chemistry. Is it?
Yeah.
Is it?
Why?
You are. But you're talking to me, that's not. What's that
Our
side
side
conversation?
conversation
Is it about chemistry? Okay. I was talking to you, dude.
The entire time.
Yeah, dude.
I was so zoned out. Man, sorry.
I know.
Weird
Yeah.
day. Sorry.
Yeah.
And
Yeah.
I've been doing you wrong.
I slept on a pull-out couch last night, so
Why?
my back
Why?
is kind of like,
Why did you do that?
it's at my parents' house.
Oh, so.
My mom is out of town, so I'm taking care of my dad and my son. You know, I have 2 children.
Lucky you.
They are wonderful, but they require work. But the Enamines, they can also do acylation. So again, alkylation is adding a carbon, right? CH3, CH2, just a carbon chain. Excuse me. Acylation is going to add a carbonyl plus a carbon chain. So the difference here is that the carbonyl is going to be, right, added together with the carbon chain. So it's still a similar reaction. Again, right, you have a leaving group, right? You have your salt that's going to allow you to do this, beta, right, attacks. Does that make sense? Leaving group leaves, right? Okay, so it's similar, but the right alkyl chain, right, is not alone. It has the carbonyl built in to it. So these are called acylation, not alkylation.
And you said alkylation was when we're adding the carbon, and this one is when we're what?
We're adding an acyl group. The acyl is the carbonyl with a carbon chain. So basically you don't get just one carbonyl, right? You get the carbonyl that's going to come from the salt when you add the water plus acid, and you also get the carbonyl that came from your acyl group, right? The one that got attacked and the leaving group left. So you actually, your product is a beta hydroxy, isn't it? Right? It has that beta keto, right? It has that ketone at the beta position. So the difference between acyl, right, is just R. Or alkyl is just R. Right? This is going to be R.
I can't see anything.
Here's one. Oh my God.
Oh my God!
Catch that. That should go on YouTube. The YouTubes. My son says.
I don't think the video needs to see it that you made it.
Yeah, we kind of.
But you're my witness that we made it, right?
A reaction.
Yeah, the video.
There's a lot of magic going on today, not just in the.
So where's your genius shirt now?
Yeah.
The video just shows you throw and then you hear like, oh, and it starts rattling. Stadium starts
Anyway,
shaking.
Alright.
an alkyl is just R by itself, right? The acyl is R plus the carbonyl, and then you're adding it. This is the acyl. Does that make sense? So there's an R, but that R is connected to a carbonyl. So that's really the difference between the two. But that, you know, the reaction is the same. You're using the enamine, you're going through the process of forming that iminium salt and then adding the water acid to get the carbonyl.
So it's exactly the same, except this one has a carbonyl that you're adding.
That's what I mean. Alkyl is just carbons. Acyl has the carbonyl as well. So your product doesn't have just one carbonyl, it has 2 carbonyls.
It's special.
So, you know, same process, but you know, the difference is that carbonyl is built in to the leaving group. So that's, you know, so enamines can be involved in either alkylation or acylation. Right? So that's it for the nitrogen part. Yeah, we'll come back around again when we talk about the Michael addition. Okay, but first we're going to talk about 2 standard again, right? These are very standard reactions. Once you learn how to do one, you can do all of them. So when we look at these now, acetoacetic ester reactions, or AAE, abbreviated there. The purpose of these reactions is to get substituted acetone. So you can get the mono substituted, right, just one R, right? Or you can get the di substituted 2 R's, okay? But really what's in yellow is acetone, right? Propanone, that's acetone, okay? Are you adding just 1 or 2 substitutions? So is this an acylation or an alkylation? What am I adding?
Carbon.
Yeah, carbon.
Just the
Isolation.
carbon, so it's an alkylation.
And then the second one.
No, it's only alkylation. The double bond O is already built into your starting material.
Wouldn't it be it's not a deep.
So you're adding R's. You see what's not highlighted is the R. That's all you're adding. So this is a type of alkylation, not acylation. Alright, so this works because the acetoacetic ester, which is shown here,
Yeah.
Yeah, I knew CO2.
there's so much side chatter.
We're talking about chemistry.
I know you are, but it's a little too much.
Everybody's all the things so bad.
Is it the weather?
Yeah.
It feels really good outside.
Yeah.
I didn't feel so good when I did like a whole loop around and I was like misting because it's so humid. It felt like summer. I'm like, I should have like planned for this. You know, shorts or something. A little too warm. But the reason this works is because the starting material, acetoacetic ester, already has acetone as part of its structure. That's really the key here. So these substituted products come from this particular starting material, which has the acetone built in. So how am I going to get rid of this? Right, that's the key. How do I get rid of this part of the molecule?
Adding
3 letters. S-A-T. All right, so how does that happen, right? That's the key. It's like, I want to do this reaction. I must use this starting material because it's part acetone already. And then the second thing is I can get rid of that, right, ester group that I highlighted there in the blue.
What's
All right.
SAT mean?
What does SAT mean? Supenification, acidification, thermal decarboxylation. S-A-T. And on the exam, you actually can just write those 3 letters and you will get perfectly correct on your mechanism. You don't have to separate those into 3 different reactions. You don't have to give me the reagents. As long as you understand when and where to use it. That's the key. It's on your reaction sheet anyways, but you don't even have to waste time figuring out what reagents to use. The important thing is that you know when and where to use it.
So we can use the SAT when we already have an acetone built in.
You can use the SAT anytime you have an ester, an extra ester that you need gone. You want to whack that ester. That's it, gone.
Violent.
I've told organic chemistry is very violent. There's lots of reactions and lots of attacks. All right, so this boils down to 5 sequential steps. So what do you think is going to happen in the first step? So I want to make this product, it's acetone, right? Highlighted in yellow. So what am I adding to the acetone? What's my substitution? The other part, right? That carbon chain. So what do you think the 5 steps are? What is the first thing that has to happen? I need to find a nucleophile, right? Acetoacetic ester is not a nucleophile all by itself. What must you add to it? Base.
Base, yes, you
Right? You deprotonate, you form the alpha carbon as a nucleophile. That's the first thing you have to do. Then once the nucleophile is there, what do you do next?
The nucleophile attacks the carbon.
Attacks the carbon chain with the leaving group, which is going to be, right, part of the second step. And then what do you do on the other 3 steps? S-A-T. It's a beauty. Easy, right? I mean, like I said, it's really standard. Once you understand the basics, you're just over and over and over again doing the same steps. Yep.
Could you draw what you just said?
I cannot. I can only use one hand. It's on the next slide. I'm just kidding. That's usually what follows, right? But I just wanted you to see that it's really, I mean, it's very straightforward. I don't really, I want to emphasize that, right? So again, first step, you have to take, right, that base, the protonate, again, the alpha carbon. Now, why not this alpha? That's an alpha carbon. What's special about this alpha? It's between two carbonyls. That's a more acidic position because of the two carbonyls. Okay, so it's always going to be, right, the carbon in the middle, between the two carbonyls. So that's something you can bet on every time. 100% of the time in this reaction, that's what's going to happen. So you see that the base deprotonates, right? So now you have your carbanion. The carbanion is the nucleophile. So it attacks your alkyl group, right? The alkyl is an alkyl halide, in this case bromine. So you're going to attack the carbon that has the leaving group. That's an SN2 reaction. All right? And now you have your R there, but you still have that pesky ester that I don't want, right? That needs to go. So what do? SAT, whack it. You're going to think about that every time you do a problem, right? So the 3 steps again, right? Supenification, acidification, thermal decarboxylation. And these are the reagents. They're in your reaction sheet, so it's not, that you cannot put those in instead of SAT, but I think that's a shortcut that might help save time on an exam and, whatnot. Now, OWL is still going to give you the reagents. So you'll get practice on that. But again, you are removing that ester. And now you have your acetone there, 5 steps. You can also, so this is the disubstituted. So if you're going to do a disubstituted product, how many steps? The first 2 got to happen again, basically, right? So it makes 7 because you got to do the first substitution, the second substitution, and then the SAT. So you want to do the substitutions all first. Everything you want to substitute happens first, and then you do the SAT at the end. So in this case, we're kind of going back. We've already substituted the first one, so we did 2 steps already. Okay, so at the end of the second step, we then add another base to, right, deprotonate at the alpha position. Okay, then that is the nucleophile, which is going to attack a new carbon chain, or maybe the same carbon chain, and you could, have 2 of the same R groups, but in this case, it's a different one. It's just a carbon chain. Right, so that's added here, so you have this substitution and this substitution, but still have to get rid of the, right, ester. So SAT gives you the disubstituted product. Now, did the order matter? The fact that I did the longer chain first and the shorter chain second, did that matter? It did.
It did, because you had to have that.
So you need more space. If you have a bigger group, you want to kind of do that first, and then the smaller group second. So OWL is picky. I wouldn't be that picky in the exam as long as you had both substitutions there. I would probably give you full credit. But OWL gets particular. So make a note that you should do the bigger substitution first if they're not the same. The order does matter. Okay. So you can do the same set of reactions with malonic esters. So instead of getting the substituted acetone, you now give the get the substituted acetic acid. And the reason is you now have, right, 2 esters. The other one had a keto, right, a ketone and an ester. You now have 2 esters. Only one of them can be completely removed. The other one, through the SAT, is going to get converted to an acid. The thermal decarboxylation only gets rid of 1 carbon dioxide molecule, not 2. So the product, when you have 2 esters, is an acid at the end. So again, you're going to get rid of this one in blue, but notice that the other one is still there, but it's not an ester anymore, it's a carboxylic acid. Okay, and you can still do the disubstitution, so that's the other one. So again, when I look at this one, was this Di-substituted, mono-substituted, right? You gotta figure it out. You see the acid, right? There's one thing that got added. So this was a mono-substituted. How many steps? 5. Same thing, right? You're just starting with a different starting material, malonic ester. So first step, you treat it with the base. You get the nucleophile. The nucleophile then attacks, leaving group leaves, SN2, and then you do SAT. But like I said, when you do the SAT in this case, because you have 2 acids, right, after the SAT, only 1 gets removed by the heat, not 2. That's just the way the thermal decarboxylation works. Only 1 mole of carbon dioxide gets removed. The other stays. Okay? And that's all we're doing today. So we will pick it up with the conjugated systems, and that's the Michael addition.
Michael Scott edition.
This is where we left off with the notes. And so we're kind of building up. Now that again, we talked about the Aldol, then we talked about the different condensations, so Claisen and Diekman, and then we talked about the Enamines as well. So we are now going to talk about another way of doing these reactions. So how else could I generate this carbon nucleophile? That's really what we're talking about. So the first part is telling you, okay, right, the key point here, right, or the trend is forming a carbon nucleophile, right? I highlighted that there, underlined in red. So we've talked about anions, right, alkynes, also cyanides, organometallics, so Grignards, organolithium, Gilmans, all of those give you carbon nucleophiles. In this chapter, we've already covered enolates, right, aldehydes, ketones, esters, okay, and then the enamines. But there's one more candidate for this, and it's called the conjugated system. So a conjugated system we've actually already talked about last semester, and it was actually something on the first or second exam. I don't know if you recall having to tell how many carbons were conjugated, right? How many? So that's really the same thing. A conjugated system is when you have a double bond adjacent to a lone pair or adjacent to another double bond. So you basically are conjugated, right? Double adjacent to something that can then move the electron. So that's what the conjugation has to do. So, or comes in to play here. So a substitution, what we're going to see, right? You can substitute the carbon nucleophile, so you can use it in an SN2 kind of reaction, or we can do a nucleophilic addition. Okay, and so the Michael, okay, is a special kind of reaction using the conjugated system. So this is a Michael, so it's a nucleophilic addition of an enolate, okay, to give you, or to, excuse me, an alpha beta unsaturated carbonyl. So where did this come from?
Where it wasn't from?
The alpha beta unsaturated carbonyl. So remember when you do an aldol, you get that beta hydroxy aldehyde or ketone, but you can actually eliminate that hydroxyl, right, plus a hydrogen of the carbon next to it, and it gives you the alpha beta unsaturated carbonyl. So the reason I'm pointing this out is because a lot of times the Michael has a step beforehand. We have to first do an aldol reaction to give you the alpha beta unsaturated carbonyl. And so it's usually combined, the Michael and the aldol together. Does that make sense?
How do you eliminate
So
the
this comes from the aldol. So you have an OH and then you have a hydrogen and you can remove water. So that's how you end up with unsaturated means a double bond.
How do you
So
remove?
it's an elimination.
How do you remove that alcohol?
Again, it's just an elimination. So, you know, just there's a base. Remember, you need a base and heat. That's all.
So it comes
And you
from
have
an
both.
elimination.
Hmm?
So it comes from the.
Yeah, that's what I mean. Like the reaction, when you do an aldol reaction, it's done in the presence of a base, and you usually have at least some heating. It's a warm solution. So that's prime conditions for eliminations to happen. So So there's, this is where this comes from, because it's going to be important that you realize sometimes you have to do this first. So you have to do an Aldol reaction first, create the alpha beta unsaturated carbonyl, and then add it to the conjugated system. Okay? So the conjugated system is, again, right, a carbonyl, a double bond, adjacent to another double bond. So this is what's highlighted right here is what would be your hint that this is going to be a Michael reaction and no other reaction. Does that make sense? That's a conjugated system in that blue square, right? It's a double bond, right? The carbonyl adjacent to another double bond, right? So how is this going to work? So basically, this is going to be a beta, right? My attack, if you look at the product, right, is at the beta position. This is the new bond, right? So the question is, who is the nucleophile? Does that make sense? So you can tell, I hope, that this is the new bond. The double bond is gone, right? But like, who attacked who, right? Who's the nucleophile in this situation, right? So who's going to be the nucleophile? So you have two choices, really, right? It can be the alpha carbon, right? And then what would happen? If this is the nucleophile, this is going to attack, this is going to move, this is going to move, and then what? Right? Does that make sense?
Yeah, so then you get a positive charge on your oxygen.
Not a positive
Or
charge,
negative.
negative charge.
Yeah, negative.
Right? But eventually, I want my double bond back. Does that make sense? Did you understand what I did there? So if this is the attack, right side, the nucleophile, it's going to have to, right, attack. This is going to have to move. And this is going to have to move. But look at the product. The product still has a carbonyl that doesn't have an alcohol, right? Does that make sense though? I'm just, again, if you look at this, right, that's the consideration you have to have. So there's really two parts to this reaction. There's going to be the nucleophiles, and you're correct. The nucleophile is, right, the alpha carbon. So you can see that these were the different groups we've already been discussing, right? The ketones, the esters, right? You can also do it with nitrile, the diesters, and the enamines, right? So we've talked about all of those. And then you have to have a receptor. Who's going to get, right, those electrons, or who's going to be attacked by the nucleophile? That's going to have to be the conjugated system, right? And it's always at the beta position, right? So you want to kind of keep this, this in mind, that there's a nucleophile and there's an acceptor. Okay, so when we look at something like this, right, again, what's going to, right, first thing, who's the nucleophile, right? It's going to be the alpha carbon, right, so the one in yellow. Okay, where is it going to attack? At the double bond, right, at the beta position, right here, not the alpha, right? Well, alpha is the next to, beta is next to that. That makes sense? Okay, and so then you're going to have a shift, and that's what's shown down here, right? So the reason this all works is because you can do these kinds of resonance structures, moving the double bonds and the electrons in your conjugated system. And it leaves your beta position as an electrophile, right? That positive charge is telling me that carbon wants the electrons. So it's going to be really favorable, right, the reaction with the nucleophile. Okay. So that's kind of, the key. But I think finishing this out is important. So let's look at the mechanism. So again, right, you have to form the nucleophile first. So of course the base comes in, deprotonates. So who's the nucleophile again? One more time. The alpha carbon, thank you, right? So see the pattern. This hasn't changed. We've been doing this all chapter and it continues here, right? But who's going to get attacked, right? Now it's a little bit different. It's not the carbonyl that's getting attacked. It's the beta carbon, right? Alpha right next to beta is the one next to that, right? And there's a shift then of these, right, double bonds. So you can see that there's some resonance stabilizing here your anion. okay? But eventually you have to close this out, right? So how do I close it out? Okay, so that's what's shown here. The base in the first step gained the hydrogen, right? So now it's the conjugate acid is going to come back and provide the hydrogen here. Right? So now it's an enol, but what do I know about enols? They tautomerize to the ketone. So you know, you have to kind of understand that there's, right, this driving force to not end as a alcohol, but to reform your ketone. So, and that's due to the tautomerism, which again, we've, you know, been discussing this for a while now, right? This preference for one, right, form over the other. That's basically the definition. And the keto form is preferred. Does everybody see how, right, this can occur? And again, Michael is a very prominent reaction also in organic chemistry, so it's used a good bit. Okay, it works very well. Does that make sense? Easiest part? No? Right, but you have to kind of see that the base, right, is getting protonated in that first step. It comes back to provide that hydrogen that you need, right? Because then that hydrogen, right, can be exchanged here. See that hydrogen? It was here, now it's here.
Because we want the ketone.
So, because you want the ketone, so the tautomerism takes care of that exchange. So, okay, so that's basically the Michael reaction, and you know, it's using the same, right, nucleophile setup that we've been using over again, but we're not attacking a carbonyl now, right? We are attacking the double bond at the beta position. Okay, so just a few final words on this. So there are a few requirements to this reaction, and one of them is the strength of your base that you're using. And so usually if you use a weak base, the reaction is slow. Okay, and so what we say is that what we get is a 1,4 product. Okay, so if we are saying that, right, this is going to be our carbonyl, it's 1, 2, 3, 4. Right, so the addition is further away, right? It's a 1,4 addition when the base is weak. Okay, now what about if you have a strong base? Okay, when you have a strong base, now the addition is very rapid because that base, right, is strong. So the addition is at a 1, 2 position, so it's going to be added here. You see the difference? This is a 1, 2, right? This is a 1, 2, 3, 4. Right? This is a 1, 4 addition. This is a 1, 2 addition. Okay, and so you have to pay attention to the base. That's going to be the key. So things like enolates, enamines are weak bases. So the reaction we just saw in the previous slide gives you the 1,4 product at the beta position. But when you have a strong base like the Grignards, the organolithiums, okay, those are going to give you attack, right, at the carbonyl in a 1, right, 2 addition. So I guess the point is, if you get the Grignard, you should still attack the carbonyl, right? Don't attack at the conjugated beta position, right?
So it should be obvious right away, depending on the base, how many, what it should have.
That's what I mean, like the base, right? The base is going to be the determining factor here. Okay, so the bases we've been talking about all chapter, enolates, enamines, okay, those are considered weak bases. They are going to give you the addition in the Michael that we just discussed at the beta position. But things like, right, the organometallics, Grignards, organolithiums, they still are going to continue to attack the carbonyl, even if you have a double bond. An alpha beta unsaturated, right? So you do have to decide what to do. And like I said, a lot of times the Michael and the Aldol are combined together. Like you see them, okay, either you have to do the Aldol first and, you know, create your alpha beta unsaturated, Okay, or you can do it after, so there's a combination, and this is called the Robinson Annulation, so this is a Michael Aldol, so you're starting with the Michael, again, right, this is your nucleophile, the alpha carbon, right, it's going to attack here at the beta position, right, move around your conjugated system, so you would get this product from the Michael, would you agree?
Yes.
Right? Okay, and then you would add the reactants, again, your base, right? And this is going to give you the aldol. Why? Because you have a ketone, right? And aldol reactions start out with either a ketone or an aldehyde. So here you have the ketone, so what you can do is actually cyclize. Okay? And so again, you have an alpha position here, you have an alpha position here. You just have to decide which one is going to give you the 6-member ring, right?
Wait, what are the alpha
And it's gonna
positions?
be,
So you have an alpha position on one side, an alpha position on this side. So this one is too short, right? 1, 2, 3, 4. That wouldn't work, right? But this would be 1, 2, 3, 4, 5, 6. So this alpha can attack here, right? The base is going to deprotonate, attack, open, gives you the alcohol, right? And then remember, you can eliminate a water and make your alpha beta unsaturated carbonyl. So again, very common to combine Michael and aldol reaction. Sometimes the aldol comes first to prepare the alpha beta unsaturated carbonyl. Okay, here's an example with this Robinson Annulation where the Michael happens first, and then you use the aldol to cyclize.
If you start out with a ketone though, would you use the aldol reaction if you have a ketone? Or?
That's what I mean. If you still have to form this, you would have to do the aldol first. This comes from an aldol reaction, this part. But obviously you can buy that reagent and then you can start straight into the Michael. Does that make sense? So you don't always have to, just depends on how you're, in your synthesis, what you decide to do with your reagents. But this comes from, right, you can make this from an aldol reaction as well. So, but the Robinson Annulation is Michael followed by the aldol to cyclize. Does that make sense?
Slowly but surely.
But again, it's the same process. You have to think that there's an alpha position, right? That alpha position is going to get deprotonated by the base. So I mean, you got to recognize the reagents and what they're telling you. So that's okay. So how do we know which one is an aldol, which one is a Michael? So how did I know this was Michael? I know it's telling me. But how would I know if it wasn't telling you? What is the key?
it's not adding to this.
What is the key? In the reagents, what's the key?
Base.
The base is in both. There's a base
Oh.
here, there's a base, it's the same reagents.
Where
Alcohol. Not the alcohol.
Where it's adding, where it's connecting.
The
it's
conjugated system.
not-
The conjugated system always gives you a Michael, right? The alcohol, you're right, is the key that this is going to be an aldol. Remember, the beta hydroxy always comes from an aldol reaction. But for the Michael, right, this is the key for the Michael, the conjugated system. The key to the aldol is the product alcohol. Aldol, right? It's making an alcohol. That makes sense. So if it wasn't labeled for you, right, you would want to look for those two signs that, right, you have a Michael followed by an aldol. So the alcohol is for the aldol reaction, the conjugated system for the Michael. And so again, back to that retrosynthesis, which, I find really, cool to be able to look at something, right, a product, and again, figure out what should I use as a reagent to make this product. And it's really what organic chemistry is all about in the lab. It's figuring out, I want to make this, how do I make it, right? So this is the product, I'm trying to make this, and so the key here is identifying acetone. So remember that acetone comes from a specific reagent, the acetoacetic ester, right? AAE. Okay, and so I know that that's going to have to be in the beginning, right? But then I look at this side. So how do I know what to do with this side? It's telling you that it's going to be a Michael. How do I know it's a Michael? Because it's a 1, 2, 3, 4 addition. Right? A 1,4 addition is going to be the key here. Right? If it was a 1,2 addition, then it would have been a Grignard, an organolithium, right? A strong base. So if you're given a product, you can kind of work backwards with the information that you know. Right? That makes sense? So again, the acetone, you know it came from the acetoacetic ester, right? And then when you look at this, look at the distance between the carbonyl, right, and the new bond that you made. It's a 1,4 distance. So that again is a clue that it must have been a Michael. There must have been a double bond here, right? Or sorry, this is the new bond. So the double bond would have to be here, right? The new bond is this one, right? This one. So the double bond precedes it. That makes sense? So if you look at a product, there are certain clues, things you should look at. Does everybody see that? Okay, so how do enamines come into play? So we've looked at enolates. So remember the enamine, right? What it's going to have going for it. Remember that there's a lone pair here. That lone pair makes a double bond, right? And then these electrons can then attack the conjugated system, right? Remember how the enamines work. So the lone pair, double bond, then these are available now to attack at the beta position. Again, this is a triple bond over here, so the conjugated system, right, with a cyanide. Okay, so it's going to give you again, right, that distance between the carbon and the new, right, bond. And of course, you know that if you add water plus acid, it gets rid of the nitrogen, the iminium salt, and it gives you a carbonyl, right? This is the iminium salt. So it gives you that carbonyl in the place of the salt. So enamines are very, good reagents for this. Yes.
And the double bond goes away from the.
Well, the double bond is literally the one that's attacking. So the new bond that you see here is the double bond.
And I mean the one from that's being attacked.
Yeah, because this one is going to conjugate back to the cyanide. So that's the conjugated system, how it works. It moves that double bond over to the other conjugated part, which in this case is the cyanide. So in the Michael, you don't produce a double bond in the product. The double bond shifts over until it becomes, right, part of the other conjugated.
Whether that being the cyanide or the double bond.
Or the ketone, right? Or it could be an alkyne. So there's options, but it moves all the way over to the conjugated system. So that's the enamines. So these are, again, also important here. So what about crossed reactions, right? So again, remember, crossed reactions are when you're starting with two different starting materials, right? Which you would agree that the Michael is a crossed reaction, right? I start with my alpha carbon, which is usually, right, going to have the alpha position between the two carbonyls, and then I have this conjugated system. They're different from each other. So there's particular base that works very well for these crossed reactions, and particularly when the enolate is present. Okay, and so that is LDA, lithium diisopropyl amide, and it shows you here what it looks like. And this is just showing you how to make it, but what you want to know is when you see LDA, okay, you should key in that this is the base. Okay, that's going to deprotonate your alpha carbon. Okay, so let's see how that works here. So using, right, molar equivalent of LDA, right, you can completely convert any, right, carbonyl containing compound, so an aldehyde, a ketone, an ester, to the enolate completely, 100%. Okay? So that means that, right, there's going to be an acid-base reaction happening here. So again, the LDA is your base, right, and you're going to have those alpha positions, right, so that's the alpha position over here. Okay? So 100% is going to be in this state, which means what? Is this good for the reaction going forward? Right? This is going to be the driving force, right? Just like when you have an acid that is 100%, right, ionized in solution, right? It's kind of the same concept. It's going to be a much stronger acid in that solution. So it's the same kind of concept here. So what would we do then? So what we're assuming is that if we have LDA, right, and it's very efficient reagent, so you can see that we do lower the temperature, so it's a minus 78 condition there, so it is, right, under control. So if you have acetone, LDA will convert all the acetone to the lithium enolate, okay, which then means that you're going to have, right, a very robust reaction with, right, your ketone, or sorry, in this case aldehyde, right? Here's the aldehyde, okay? And then of course you just have the water to do what? Just propane, right? That makes sense? So this is a way of driving the reaction. LDA is a great base, okay? It forms 100% of the enolate ion that you need to do these reactions. So you'll see this a good bit in this chapter, okay? Al likes to use this one a lot. Okay, so let's say that we have ketones, right? Two sets of non-equivalent hydrogens in the ketone. Is the formation going to be regioselective? Do I care which of the alpha? If they're non-equivalent, right? Of course, if they're equivalent, only one of them will react. But what if they're not the same, right? Does it matter where? The answer is yes. Okay? But yeah, it does matter. But the degree of where that regioselectivity or whether that regioselectivity is going to matter has to do with the experimental conditions. So yes, regioselectivity matters, but depending on the reaction conditions, you may or may not see that represented in the products. So let's see what that means. Okay, so let's say that you have 2-methylcyclohexanone. So this is it right here, right? You added LDA, okay, in excess. So now I have a more base than I have ketone, right? So that's the reaction condition. Does that make sense? So the base is in excess. Okay? So when you have that, you notice that, okay, I have two alpha positions, right? This one or that one. Would you agree? They are not the same. I have a methyl group over here, and I have two hydrogens over here. Does that make sense? They're not equal, so they're non-equivalent. So the question is, am I going to see a difference, right?
Yeah.
Is it going to be 50-50? Right? That's the question. When the base is in excess, notice that you do get a preference for the side that is least substituted, has more hydrogens, right? 99%. Only 1% goes the other way. Does everybody understand? There's two alpha positions that I can choose. When the base is in excess, lots of base, it's going to choose, right, 99% of the time to go with where there's more hydrogens.
Because it can pull more hydrogen.
Okay. Does that make sense? So, all right, now what if my ketone is excess, right? Ketone. So this is the one that is in more, right, larger quantity than the base, right? So the base is my limiting reagent now. So now notice that what I get is what? 90% the other product. The one that is more substituted. Ponder on that. So what is really the difference between one and the other, right? So here I have more hydrogens. Here I have more carbons, right? So you would say this side is tertiary, right? That's more stable. So down here, when I don't have a lot of base, right, base is not in excess, I must have a very stable carbon, right? When I have a lot of base, it doesn't matter. There's going to be so much base. The base is just going to get to wherever is easiest to get to. Wouldn't you agree where there is no carbons, it's going to be much easier to get to? Here it matters. The base has to be selective of where it goes. It's going to go to the most stable position, right? Here, there's so much base, it doesn't matter, right? Stability doesn't matter. It just matters, right, fast. I want to get that done, right? I have a lot of base. So that's really, right, two different things going on. There's thermodynamics, which has to do with stability, and then there's kinetics, which has to do with rates, speed. Which one is driven by speed? Which one is driven by stability? The first one is speed, the second one is stability, right? So this is kinetically driven, this is thermodynamically driven. And so the same reagents, right? Starting with the same two things, but the reaction conditions completely change, right? What is driving the product. So that's what it says over here. So there's two options for this, right? You have the kinetic option, which is rate, speed. The fastest the rate, right? The fastest rate wins, right? It's a race. Okay. Thermodynamic, though, is really about equilibrium, about stability, reaching equilibrium, right? Being in control, right? And so thermodynamic control is really due to the stability. So the more stable your alpha carbon, okay, more likely that the product is going to be at that position. Tertiary is more stable than secondary. Does that make sense? Thermodynamics versus kinetics.
Yeah.
And again, this is more physics than chemistry, so I'll leave it at that. But you know,
Maybe
I
you should teach
got a
us
C
physics.
plus in physics, so
should
you don't
teach
want
us.
me teaching any physics.
Trust
that's what I'm
me,
saying.
you probably want
I do not go there. But I do know enough to follow my chemistry steps here. But so it's again, it's just showing you that, right? This is the more stable position, right? So taking that hydrogen here, okay, is going to be again a thermodynamic driven process. So that's just what this is showing here. But the equilibrium, right? That's driven by equilibrium. But what if it was driven by rate, right? How fast are you going to make your product? Okay, so it's all based on speed. Okay, and of course, in order to make the product, the first thing is to remove the hydrogen from the alpha carbon. The base, right, deprotonates the alpha carbon. And so when the carbon is less hindered, right, there's more hydrogens, that's going to be an easier place to go, right? Which means the reaction is going to happen faster. There is no need to reach an equilibrium in this reaction. It's all about speed, rate, okay? So the kinetic control. So that's going to give you, right, the least substituted product. I didn't put the product on here, but you can go back, right? So again, if you write down, right, this is kinetic driven, right, and this is thermodynamically driven. And that's it. That's 19.